Okay. Some quick logistics before we start. So the poll winners for when office hours will be Tuesdays from 3 to 5 and Wednesdays from 4 to 5. So it'll be a total of 3 hours of office hours, with the exception being today, which I'm in Dayton, Ohio this afternoon for a meeting. So I will not be at office hours today. I will be there on Wednesday. Okay. So yes. Tuesdays from 3 to 5 and Wednesdays from 4 to 5. This is in my office, which is E542 Scott Lab. And I'll send this out via email as well. And update the syllabus, make sure that's all uploaded on Carmen, etc. All right. So where were we on Thursday, right? So Thursday we got partially through basically just the background and review of ordinary and partial differential equations, right? So we got through all the ordinary differential equations, components of it, and now we're getting into the partial differential equations. And the first thing that we started looking at is, we motivated the use of a Green's function or a convolution kernel using ODEs and the ways in which you can solve ODEs using a convolution kernel. And now we're building up the idea of how you can use convolution kernels for PDEs, even though they have a slightly different form, but the same idea still holds. And so we said that the fusion equation has this kernel, or what's called a Green's function, which is given right here. And we looked at some of these basic properties for this. Okay, we looked at what does this look like, and it's important to keep in mind that time here is in two locations, right? Here in the denominator of s, and here in the exponent of the exponential as well. Okay, so unlike the convolution kernel or the Green's function for an ODE, which is purely dependent on time, we have time here, and also we have a dependency on x. Okay, so every form, at least for the diffusion equation, this convolution kernel or Green's function is going to be dependent on x. You can see that this looks like a normal distribution, which you should have seen in a statistics class, or a variety of other engineering classes you may have seen, but now it's also a function in time, right? So if we look at, again, going back to the equation, if you have time is equal to 0, right, so that means this exponential is going to, it's basically, if you look at the limit of this, but basically you have a time in the denominator. This peak here gets infinitely high and infinitesimally wide. As time increases, then this peak is going to continue to decrease, and then the variance of this Gaussian distribution is going to widen. Okay, and we'll see how this can be applied to different applications in a second, but here's the general form of the Green's function for the diffusion equation. Now, the Green's function is different depending on what type of partial differential equation you're looking at. Unlike the ODE case, which they're basically all the same, PDEs are not so simple. Okay. Okay. So we started this example here, and this is like the most basic PDE you can come up with. If you take a graduate class in PDEs, you'll be solving equations like this within just a few weeks. Right? This will be the first thing you would ever see. So we're going to start here as well. So consider an infinite rod with thermal conductivity K. The rod has initial temperature profile, which is given here. So what this is saying is that this rod, somehow you were able to acquire an infinite rod, and you were then somehow able to impose a temperature profile from negative L to L that has a value of 1. Okay, so this is just kind of a dummy example, but we'll start to look at how this can be applied to the problem of extrusion in additive manufacturing, where you're going to have a material that when it's in the heated nozzle is going to have an elevated temperature imposed upon it, and then as it leaves, it's going to be exposed to something that is not elevated or ambient, right? And we'll see how this basic formulation can be applied to that with a little bit of work, but this is the foundation of it. Okay. So what we have here is we have this temperature profile given here, and what we're trying to do is find the temperature Ux of t for all x ranging from negative infinity to infinity. So this infinite rod, we want to know what is the temperature at every position along this rod, and for all time greater than or equal to 0. And then getting back to what we talked about on Thursday, this is the diffusion equation, which describes thermal diffusion in this process. And we know that whatever solution is, Ux of t, it must satisfy this PDE. It must satisfy these initial conditions as well. And since we're looking at the infinite domain, we don't have to worry about boundary conditions just yet. The assumption of the boundary conditions is basically that the derivative with respect to x is equal to 0 at the boundary, would be the main assumption here. Okay. So going through this, this is the diffusion equation. So we are going to assume that this Green's function applies to this system. So the Green's function for this, because it's a diffusion equation, will be exactly what we had before, written out. So U of x comma t is equal to 1 over square root of 4 pi kt integration from, negative infinity to infinity, e to the negative x minus y. I'll talk about why it's x minus y in a second. And then we have Vy. Okay, so comparing the solution with the Green's function here. All right, so here is the Green's function, and this is in terms of just regular x here. The solution is going to be based off that Green's function, where we're now integrating from negative infinity to infinity with some integration factor, dy, and multiplying by the initial conditions. All right, so this is the property of how we solve, or this is the basic way in which we're going to solve PDEs using Green's functions here. All right, for non-zero initial conditions. We haven't gotten to the case where this is a non-homogeneous partial difference equation yet. That'll be a little more complicated, but this is going to be the method which we're going to solve this. So we're looking at what is the Green's function for this differential equation, apply an integrating factor, multiply by the initial conditions, and then integrate from negative infinity with respect to that integrating factor here. Okay. Any questions about that basic idea on how we take the Green's function to a solution? And I haven't gotten to the solution yet, but this is where we're starting. Okay. All right. So we know, though, that phi of x is equal to 0 for a large part of this domain from negative infinity to infinity, right? Okay, so we can actually simplify this. We know it's 1 for absolute value of x less than or equal to L, and it's 0 for anything outside that, right? So I can rewrite my PDE, or my solution So now I look at the range from negative 1 to 1. Okay, in this range, phi of y is equal to 1. So now I just integrate with respect to dy. All right, so it's a reduced domain. Sorry, I have a mistake. This is from L to negative. Sorry, this is from L to negative L. All right, I just read this incorrectly. Okay, so then this gives me, I can now take this integral, which I'm not going to quite do, but I'll show you how this can be simplified in a second. But once to do this integration, we can use the substitution rule. So I'm going to define this variable p, which is equal to x minus y, square root of 4 kt. And if I want to apply the substitution, right, I need to substitute in, so everything that was a y, the y's will cease to exist, right? So I can do dp dy is equal to -1 over square root of 4 kt. And now with this information, I can then plug it back into my integral, right? So that gives me u of x of t all right, because we have this square root of 4 over kt, what that does is actually cancels out some of the coefficient here, not all of it, right? It doesn't cancel out the pi, but it cancels out the rest of it. So -1 over square root of pi. I'll get into what the limits of integration are in a second, but now I get e to the negative p squared dp. Yes?
We always assume that x and y are independent of each other.
So yeah, so we just have an integrating factor y.
Yeah.
Yeah, so these are completely different variables. Yeah. So yeah, so x is because we're looking at, just to go back to your question here. So u of x of t, x is literally the coordinate along here. Y is an integrating factor, right, which has the same units and everything, but they're independent. So you can think of x is the position along here, y is the integrating factor. I'm going from some sort of position y, which ranges from -infinity to infinity, so that's a y that goes along this direction. So along the same direction, but they're completely independent variables. Okay. All right, so now we have this equation right here. The limits of integration, this is standard substitution, which you learned in the calculus class. Limits of integration now become x, whoops. Sorry, my computer was backing up as we were working here. Now limits of integration become x plus L for the lower limit of integration and x minus L for the upper limit of integration. Sorry, I got a little cramped in there. Okay, who has seen this integral to e to the negative p squared dp before? Has anyone seen that in other classes? What do we call this function? Air function, right? Anyone else heard the air function before? Okay, so air function. So the first thing to note is that ux of t doesn't have a closed form solution. We can't just write this out and it's going to be some nice polynomial or something of that factor. So it's the air function, which is given by ERF of x. And so the air function here is defined by 2 over square root of pi integration between 0 and x of e to the negative p squared dp. Okay, so we have something that looks a lot like that, not 100%. We can use some properties of calculus to get this in the form where it will look exactly like the air function, but we have something very close here to being the air function. All right, some important properties of the air function. It's an odd function, so we have this property. And just like sine and cosine, you can't write as, say, a polynomial or some sort of simple function, but MATLAB and all these other computer programs have essentially either Taylor series approximations to this or lookup tables that have been defined to calculate the air function. So you can use the MATLAB function ERF to solve this for you. Right? So as long as we have some sort of function x here, we can evaluate the air function. All right, to give you a sense of what the air function looks like, okay, so this red line here is our air function for x. And so if we're saying air function of x is the coefficient integration between 0 and x of e minus p squared dp. So for instance, if we want to know what is the air function for x is equal to 1, we would go to this chart, or a computer would do this for you. It would integrate between 0 and 1, and it would give you an air function value of, I'm just approximating here, like 0.82 would be where that would be here. Right? Just to note, this is e to the negative x squared. If you want to know what this function that's being integrated looks like, but this is the air function. Some other important information, basically as x gets really, really large, the error function converges to 1. As x gets really, really small, error function converges to -1. Okay, so basically think of this, if you've never seen this before, think of this as sine or cosine, right? Something that you can't really write an expression that's in simple polynomial form very easily for sine and cosine unless it goes in infinite series, but you do this all the time with a calculator or MATLAB, etc., right, for the error function, right? For those of you who haven't seen it. Okay, so going back to our problem at hand, right? So we have, should I go 2 back? Right, so we have something that looks a lot like the error function here, and just like what you would have learned in any calculus classes, you can now split this integral up in 2 different pieces, right? So I can rewrite u of x of t as equal to -1 over pi, or -1 over square root of pi. Limits of integration being 0 at the top, and then my lower limit of integration at the bottom. And then the other part of it. Okay. All right, and then another manipulation which you would learn in a calculus class before is I can, if I want to make this look like the error function, I need this function to be going from 0 to some non-zero number, right? So I can then, doing that operation is just multiplying by a -1, right? So this would be the manipulation. This coefficient -1 turns to 1 on top. I can then flip the limits of integration. The second one I don't have to change. That's already in the form of the error function already. Okay, so now I have 2 basically added terms there in the form of the error function. And so then solving this, I ran out of space here, so I'm going to write it here. The solution u, whoops, u of x of t is equal to 1/2 the error function for my argument. So my upper limit of integration was x plus L over square root of 4k t minus 1/2 error function. My upper limit of integration for the second term here. All right, and that's my solution. All right, so what do we have here? So we know that ERF, oops, has this standard form. If I change the argument, I'm just basically evaluating this at different x's and different t's, right? So nothing too more complicated than that. Think of this as just some sort of dummy variable. Okay. All right, so I can evaluate this in MATLAB or whatever, Mathematica, etc., whatever program you want to use, but this would be our solution for this pretty simple PDE. We can now take a look at what this looks like, right? So we said that this is the case. I just plotted this for the case of L is equal to 1, K is equal to 1 here. All right, so we knew that the initial condition was that basically u of x of t is equal to 1 between negative L and L, right? So this is between -1 and 1 if we set L is equal to 1, right? So we see that this satisfies the initial condition. So you have this infinite rod, its temperature at the ends is equal to 0, temperature in this small segment between -1 and 1 is equal to 1, and then from there on out, heat diffuses, right? And so the hot areas become less hot, the low temperature areas become more hot because that heat diffused from the hot areas to the low temperature areas, and so then we have this diffusion, which looks like basically Gaussian. But then we have, as time increases, then the heat diffuses and spreads out from there. Would be the solution for this. We have a video that we can run. For some reason, this doesn't want to. All right, let me open it. I don't know why this isn't allowing me to play it. We'll try not presenter mode and see if this works. I don't know why it's not playing. And I don't know why the projector shut off. Let's see. All right, so I'm getting, for some reason, I'm getting a cannot play media error here. So I'm going to pull it up. Don't know why it's not working. Okay. Okay, so this is the video then form of this. So this would be then the temperature of this rod, basically diffusion time. For some reason my laptop is playing this back in a choppy form. I don't know why. It would actually be pretty smooth. We can replay that again. So this has been smoothed out. Basically, this would be the diffusion of temperature then through this rod. All right, so we see that as decay, temperature in the middle, increase in temperature everywhere else. Right? So if we were to take the time out to infinity, then it would diffuse even more, but it would be slower, right? Because the temperature gradients would be lower as they go on. Okay, all types of computer issues today. All right. Okay. So that was one example. That is for the infinite domain. If we're talking about additive manufacturing processes, it's really tough to think about what the infinite domain looks like. Right, we're talking about processes that are confined to a finite space. So oftentimes we're going to look at smaller domains here. And so say, for instance, we have boundary conditions that we care about. And we have, now instead of the infinite domain, before we said that x ranged from negative infinity to infinity. Here we have x ranging from 0 to infinity for positive time. I switched the variable here. You'll see why in a second. But for now, we just have v of t instead of u. sorry, v of x of t is instead of u of x of t, but it's just a change in variables. So we still have some sort of initial condition for v at time is equal to 0, and now we are specifying a boundary condition. So we're saying at this boundary of x is equal to 0, we're saying that the value is always equal to 0. Okay, so boundary conditions. This should be review for everyone, especially anyone who's taken a class in PDEs, but you've seen similar concepts to this in, say, solid mechanics classes, etc. So if we say that we have boundary conditions for solid mechanics, this would be looking at a beam that's bending, and we can say, we can parameterize this or state what the deflection of this beam is over space and time. And there are a bunch of different boundary conditions you can look at. One is called the Dirichlet boundary condition. So if you've never heard this before, you should get used to this terminology. But what this is saying, we have a Dirichlet boundary condition here and here. So what we're saying is that the deflection of this beam at the position 0 is equal to 0, and at the position L is equal to 0. All right, that would be an example of the Dirichlet boundary condition. So in terms of, we'll get into thermal examples in a second, but that would be saying that the temperature at some boundary is held to some value, some temperature. You can have free boundary conditions, so that's a lack of a boundary condition. You can have mixed boundary conditions, sometimes called Cauchy. So this would be imposing both the Dirichlet boundary condition, that the position is equal to 0, and also what's called the Neumann or Newman boundary condition. This is saying that this is rigidly fixed, or it's cantilevered out. It's saying that the derivative of this position with respect to x is equal to 0. So that means that at this boundary, the slope of this beam is equal to 0. Here, which you probably see in solid mechanics classes before. This would be, again, this would be a Newman boundary condition. So these are mixed. And then this would be an example of Dirichlet Newman as well. For thermal systems, we'll look at this in terms of, say, for instance, you have an infinitely large block, and this block is at some sort of temperature. We'll call this an isothermal bath. This would be our Dirichlet boundary condition at the position of x is equal to 0, and saying this is T naught. Newman boundary condition, if we have an insulated edge. So that means that heat, that should be is equal to, so it means heat transfer across this boundary is equal to 0. This would be that, or also that the change in temperature with respect to x at the position L is equal to 0, and then you can also have mixed ones as well. I'd say this if we say. All right, so this is how we're going to look at boundary conditions for this problem. We can then apply this to some of our problems here. So this is going back to the PDE that I say we're going to look at. This is the diffusion equation. It's on the half domain, or half infinite domain, going from 0 to infinity. And we're now imposing the Dirichlet boundary condition on this. So we're saying that take a rod that's of half infinite size, so it's ranging from 0 to infinity. We're going to impose some non-zero temperature on this rod at time is equal to 0, just like we had in the previous example, but instead of then allowing and solving the solution, we're going to look at the case where now we are holding or enforcing that the temperature at the origin is always equal to 0 for all time greater than or equal to 0. Does that make sense? Okay. All right. So to do this, we're going to use what are called the methods of reflection. And so the methods of reflection for the Dirichlet boundary condition is what you do is you actually you impose what's called an odd extension for Dirichlet boundary conditions. All right. So you say that well, basically we want to solve our PDE on the infinite domain. So that means we can apply, for instance, we can apply then convolution kernels, Green's functions, etc., to this problem. And so we're going to look at the infinite. We want to apply this to the infinite domain. The way in which we modify the system so we can study this on the infinite domain is we say we have an odd extension. And so say, for instance, we have some sort of initial temperature profile phi of x. The odd extension is writing basically the complement to this for x less than 0, which is an odd extension. So an odd function satisfies that. So odd function satisfies that phi of x would be equal to negative phi of negative x. That's a negative sign, not a positive. Okay, so we apply this odd extension. This would be then its odd complement to that function. And now this means that this odd extension covers the entire line here. Also note that this satisfies the Dirichlet boundary condition at time is equal to 0, right? So this odd extension is basically, if you look at the limits of integration, or sorry, the limits of this equation, this is not greater or less than or greater than or equal to or less than or equal to, right? At 0, this odd extension has a value of 0. Here. For the Newman boundary condition, we apply what's called the even extension. Right? So as opposed to the odd extension, if we look at how the plot changes, this is the even extension. We have our initial condition. We just reflect this initial condition across the x is equal to 0 axis and apply this in a very similar fashion. And so now this, again, covers the entire line. We can now solve our diffusion equation as before. Yes, Nate?
So we just solve the diffusion equation of this modified boundary condition for the whole line. And we just start x less than 0 as from the domain, and then whatever we get left is matching our original boundary statement.
Yeah. So I'm going to do an example. I think it would probably answer your question in terms of the procedure, but exactly. So we're going to basically, we know that our domain from the problem statement is between 0 and infinity. Right? We're going to, given this boundary condition at this limit of the domain we're looking at, we're going to basically apply methods of reflection, which depends on your boundary condition, that now expands your domain to be the entire line, negative infinity to infinity, and now we're going to solve this, but then we're going to only care about the domain that we initially specified. So we're not going to plot negative x when we report the solution. Does that make sense? Okay, so let's look at an example. I think that'll maybe firm up this question a little bit. Okay, so consider a semi-infinite rod with an insulated edge. Right, so insulated edge, we said before, that's the Newman boundary condition, right? So we're saying that no heat transfers through this insulated edge. Insulated edge at x is equal to 0. Thermal conductivity K again. This rod has initial temperature of 1 over this domain. So we're saying that initial temperature is 1 from the domain of L over 2 to L, and 0 for everything else. Now find the temperature for the semi-infinite domain. Okay. All right, so going back to the ideas of this even extension. Okay, so if this is phi of x for positive x, right? We're going to do an even extension, which is basically just reflecting this function about the axis of x is equal to 0. And now this becomes from negative L to negative L over 2. This function has a value of 1 as well. So if I had to write this out, I would say that phi even of x has 5 different parts. It's 0 for x greater than L, 1 for x between L over 2 and L, 0 in the middle domain, next domain, and then the very last one. Okay. Any questions about that? Okay, so this is what I just drew right here. All right, so now if I look at, now this covers the entire line, right? And so I can then look at my solution for u of x of t. Will be limit from negative infinity to infinity of my Green's function, which I said is a general form. So my Green's function is generally noted by this source function. This is what we went through on Thursday. We have our integrating factor y. Okay, so since x now covers the entire domain, or the entire domain is now from negative infinity to infinity, I can write this, and then I just know that phi even of y is equal to 0 for some portions of this domain. So I can get rid of this infinite integral and make it a determined integral, or set integral. So this is going from now negative L over 2 to negative, sorry, screw up my limits and integration just a little bit. Doesn't matter, but okay, so now that I can fill in my actual form of the Green's function, this is exactly the same as the previous problem. Okay, so you can see that this problem has now become very similar to the problem we just looked at, right? Almost exactly the same form, and we have these limits of integration that we have to deal with, but we can deal with these just like we did with the previous problem, right? Okay, so we're going to apply the same substitution. So substitution P is equal to x minus y over 4kt. Sorry, square root of 4kt. Okay, and this simplifies our problem. Negative 1 over square root of pi. Sorry, I accidentally deleted all that. Okay, so then just note that this is a little bit different than previously. We now have, say, x plus L over 2, x minus L over 2, because of our, basically, domain for our initial condition was changed a little bit, including L over 2, right? So small changes. Applying the methods almost identically to what we did in the previous problem, our solution now becomes, just skipping a few steps here, the full work is in the notes, but the solution now becomes negative 1/2. And then 4 summed error functions. So I think you can probably see where these are coming from. We have an error function coming from this limited integration. One coming from this limited of integration. This one. All right. One thing I forgot in the previous example. So we went from the half infinite space to the full infinite space. We now, no, it would have been fine in the previous example. But, one thing that we need to consider here for this example is that U is defined on the full line, right? So we need to be careful in how we report this answer. To properly report this is that V, which is what we originally wanted, is equal to U of x of t for the domain x greater than 0. So in this even extension, we basically projected the initial conditions across the x-axis. This solution here, we could basically throw this in the computer and get a solution for negative x, but that is outside the domain that we should consider, right? So if we're going to then look at the original solution, we want to find V. This is for x greater than 0. All right, so U is a solution for the entire line, V is a solution for the half line. Any questions you may have right now? Okay. So taking a look at what this looks like. So here is, again, time is equal to 0. This is very similar to the plot I showed you before. This is for L is equal to 1. K is equal to 1 as well. So again, looking at the initial conditions, time is equal to 0, right? Time is equal to 0, we're saying that the temperature is 1 between the domain of L over 2 to L, right? Notice also I'm not showing x less than 0, right? That's not part of the solution. As time increases, right, we see that then heat basically diffuses through the rod. Temperature is then basically decreases in the hot area, increases in the cold area. And the other thing to keep in mind here is that our Newman boundary condition is held, right? So if we look at this, the slope of all these lines by how the boundary conditions were set should be equal to 0 if it's a Newman boundary condition. Right? And you see that this is the case. All right, so everything checks out in terms of kind of the checks you should be doing to make sure that your solution looks correct. Initial conditions are satisfied, boundary condition is satisfied here, everything's good. We'll see if this video plays. Probably unlikely given the previous one didn't. No? That's unfortunately not how this thing works. So if one of these things on, it's always on. So I have to pull it up here. All right, this may work. Okay, so here's the video of this progressing in time. No, okay, that's not going to play either. Cannot play media. All right, let's find this. All right, so here's the raw video from this. All right, for some reason it's always choppy the first time. Let me replay this. All right, so this would be then the temperature diffusing out over time. All right, play that one more time so you can see it. But as you can see, I think the one thing to keep in mind here is if you look at the temperature at this x is equal to 0, the slope of that temperature is always equal to 0 as well, regardless of what time we have. I think this is a good time to do our daily 5-minute break. To break up the class a little bit, we'll be switching into now non-homogeneous PDEs in a second. So we'll just reconvene at, I guess, 10:52 or so. Sorry? Okay, it's going on. All right. So I'm up for tenure right now, and that's why Dr. Eldemir is here observing, so he can report back that at least through half the class it looked okay, I guess.
How much weight does species carry opposed to research?
I wish I knew the answer, but
Because you can split your time based on that.
yeah.
If it's like 10%.
I know, so what I've been told is that you can get tenure by being an average or even below average teacher if you have excellent research, but you can't get tenure if you're an excellent teacher but have below average research. Okay, so I'm going to backtrack a little bit back to ODEs for a second, just to make a point. So, well, before I do that, the reason why I'm backtracking just for a second is we want to look at now non-homogeneous PDEs. Right, so these are PDEs. Before we saw the homogeneous PDE, this was equal to 0. Non-homogeneous PDE, this PDE is now being driven. Right, so this is going to be important for a lot of additive manufacturing processes are has essentially energy sources in them, whether that be a laser, electron beam, heated nozzles, whatever. This is driving energy into the system, right? And we can, these are usually controllable inputs, so we can actually specify, let's say, f of x of t will look like, right? So a lot of the PDEs we're looking at are driven systems, so we need to look at this case. So if you recall, we were talking about ODEs. We said that there are many solutions to solve ODEs. One that you may not have been too familiar with is this form right here. Right? We can separate the solution in terms of the homogeneous solution and the non-homogeneous solution. And this non-homogeneous solution portion is always convolution. All right, so this would be this e to the at. This would be, for this particular ODE, would be the Green's function here, which is simply the solution to the impulse response of this function. So this is saying this ODE, if I hit it with a function that has infinite high intensity over an infinitesimal duration, look at my response. This particular one has this solution, e to the at. Actually, I need to modify this. Is actually, oops. I had a mistake, actually. I need to fix my notes on that. This is e to the negative at is the solution to this. Okay, so that's the Green's function for this ODE. This is what's called convolution. For those of you who take a digital signal processing class before, maybe in your systems class you saw as an undergrad or as a graduate class, you may have seen convolution, which is an integral. Right, I want to go through convolution here in a more visual sense, so you can see this if you've never seen this before. Okay, so take, for instance, this ODE and solve this using convolution. First off, the impulse response of the system is e to the negative at. So I'm not going to go through that, but that's a pretty standard definition for a first order ODE. But this will be our impulse response. And so what does this look like? It's this function. All right, this is a time constant of a, right? Or 1 over a. This is a decaying function. This is intersects at 1. So that's the impulse response for this particular ODE. If I want to know then the solution here, I may have two components. I may have y of t is going to be e to the negative at, or y0, plus then the convolution integral here. Sorry, I was using terminology I was more familiar with. This is g of t. This is then our non-homogeneous term. Okay. So what does this look like here? So this g of t looks like this function. All right, so g of t is equal to 1 for time is between 0 and uppercase t. and it's 0 for t greater than t, right? All right, so then the next question is, I'm going to do this visually. You can actually just run this integral if you wanted to, but I think it's important to think about this from a visual perspective as well, is we can, sorry, I made a mistake here as well. This is g of tau. Let's look at this in terms of g of tau, our integrating factor. Okay, so this is g of tau. If I now look at what is g of negative tau, right? Because if you look at the argument to g of t, it has negative tau in it. So as we integrate in the direction of tau, we want to understand what it is, actually g of negative tau. We'll handle what this t does in a second. If we look at g of negative tau, it's this function, right? So anywhere, basically just reflects this function about the x is equal to 0 axis, or tau is equal to 0 axis, right? And now if I were to know what is g of t minus tau, that's a q. Okay, that's simply then the translation of this function. This is t. The leading edge of this function is t. The trailing edge of this function is t minus uppercase t. Okay. All right, so what this convolution integral is saying is I have some sort of impulse response, right? And now I can convert this to be, with respect to our integrating factor is tau. This is h of tau, right? I have a solution y of t is equal to the integral between 0 and t of e to the negative a tau g of t minus tau d tau. And so what this is saying, if I care about y is equal to y at 1 second, what I'm doing is I'm integrating the multiplication of these two functions over the domain between 0 and 1, if I want to know y at equal to 1 second. If I want to know y is equal to, or what is y at 2 seconds, then I'm integrating, say, for instance, the multiplication of these two functions, where this leading edge is 2. And then this trailing edge may be no longer 0 anymore in terms of that factor. So you can think of this integration as actually sliding this forcing function along the domain of tau. And Wikipedia actually does a nice job with this. I don't know if you've ever seen the Wikipedia page for convolution before. It's not very large. How do I get that bigger? Okay. So you can think of one function sliding past the other and integrating. So this will repeat in a second. You see there's no overlap between the two functions until now there is. This is the integration over this area. Now the integral gets smaller as this no longer overlaps. All right, so if you want to go back and you're basically in between classes and look at the Wikipedia page, it actually does a really nice job of visually showing it. Better so than I can do just by drawing a bunch of these functions here. But visually, that's what's happening, right? So we have, as t gets larger, this function g of t minus tau is sliding along, and that changes our integral. Okay? So if we now look at how to write y of t, we have now two domains. Okay, so for t in the domain of 0 to uppercase t, we know that g of basically g of tau in that domain, or g of t minus tau, is equal to 1. So I'm saying that y of t is the integral between 0 and t, e to the negative a tau d tau. Okay? So in this domain, I get negative 1 over a, e to the negative a tau, evaluated at 0 and t, which is going to give me then 1 over a. Okay, so e to the, basically, two parts. Let me not skip a step here. I'll keep the negative coefficient out front. Negative 1 over a, e to the negative a t, minus e to the a t tau evaluated at 0 is equal to 1, right? So I get this equation for this range here. If I look at the range of t greater than or equal to uppercase t, my limits of integration are a little bit different. So this function is only equal to 1 over this range. So again, solving this integral with different limits of integration. Sorry. I have an error here. Let me fix this. This is tau. Okay, and then here's my solution here. I guess I should specify this is the particular solution for both of these. So it has two different domains, and that's because our forcing function is discontinuous, or is not a continuous function, so then we have a discontinuous output of our system. Okay. All right, so that's convolution in kind of a visual sense. We're going to be doing the same thing for non-homogeneous partial differential equations as well. We won't, the very first material we're going to use in AM is not going to use this, but we'll get into this later when we have more complex forcing functions. But the main thing I want to point out is that we have, this is our non-homogeneous term here. So everything looks almost identical to what we had before. We're going to have, just like with the ODE case, we're going to have a homogeneous solution. This is what we did before. This is what we did already. Right? This is the response of the system to non-zero initial conditions. Right? We're looking at the cases of the two rods with elevated temperatures. Right? So this is exactly what we did in the previous examples. And now we're going to have our non-homogeneous part of the solution. We're again going to use Green's functions. So here's the Green's function for, and this is dependent on our PDE, but say for instance this is a diffusion equation. So we're going to have the Green's function for diffusion, and now we're going to have our non-homogeneous term, and we're going to do both integration from negative infinity to infinity with respect to y, and integration between 0 and t with respect to some integrating factor s. Here. So it's going to get a little bit more complex. We're not going to get in, I just wanted to show this for now. We're not actually going to leverage this until, I don't know, probably 3 or 4 weeks from now. I wanted to introduce this idea that ODEs and PDEs are fairly similar and that you can break them up into this homogeneous and non-homogeneous solution for them. Okay. Green's function for diffusion equation with infinite boundary conditions. And so if we have reflections, etc., we need to consider that using the methods we already talked about. And this is convolution in space, convolution in time. Okay. Ideas, again, getting back to Green's functions for one-dimensional problems. So thus far, we've looked at the diffusion equation, which I'm not showing here. But some that you may have seen before is the wave equation, right? This is the wave equation, which you may have seen in the PDE class. The Green's function is the solution or the impulse response of the wave equation, which is here. This is the Heaviside function, or also is called the step function. You may have seen before. This is the Laplace equation, etc. These are different PDEs. This is not an exhaustive list. There's actually whole books you can find that have like every single Green's function that people have ever found in like the history of mathematics. But this is just kind of a sampling of them. So let's get into actually using this. So we're going to start out in 1D again, and we'll get into a 3D example quite quickly. This example is going to take actually quite a while. So I'll only be able to start this, and then we'll have to wait till Thursday to get through this completely. Okay. So before we looked at having an initial temperature profile, we're going to simplify this. We're not going to worry about this for now. We're just going to say that the initial temperature profile on this rod is 0. And we are going to put an impulse of energy. This is, I don't know if you've ever seen this shorthand form. This is the impulse function. So sometimes we just denote the impulse function by an arrow going up. And that's just made to look like the impulse function, which is infinite energy over infinitesimal time, which is like a ray, right? Okay, so what we're doing here is we have a rod, and we are putting an impulse of energy at a specific location. This location is given by Vt. So we have a constant velocity, and we're now changing where this impulse is put, right? So at time is equal to 0, the impulse is put at the origin of this rod. As time increases, just moving linearly across this rod and putting energy into the system, right? So I think you may understand where I'm going here. This would be like a laser scanning across the surface of the rod, right? Which is going to be very applicable to additive manufacturing. Okay, so basically, a laser is a lot of energy in a very small spatial region, right? So anyhow, we're basically sweeping this laser across this rod, and we want to know what is the temperature profile on this rod in time. Okay, so to do this, though, we're going to actually have to change some coordinates here. And so we're looking at this equation. I'll get into the change of coordinates in a second, but this is going to be driven by the diffusion equation. Okay, so we have a two-dimensional Dirac delta function. The center of this Dirac delta function in space is Vt, and then we're indicating 0, saying that this thing is always on, right, if we do this. Right. So always saying that this function is on. So it's a laser dragging across the surface. We have initial conditions. Zero to 0. So just think of this rod as being at 0 Kelvin, extremely cold, or gauge temperature, however you want to think about this. Right. Okay. So then our problem is here, we want to find u of x of t at steady state. And this is a little bit of a misnomer. You'll see how this changes in a second. There is no steady state for u of x of t, but I'm going to do a change of coordinates to make sure the system does have a steady state. Okay, and so to do this, instead of looking at our variables which are defined in x, we're going to do a change of coordinates. Is we're now going to follow this laser. So we're going to look at basically a coordinate system that is centered on the center of this laser. So instead of saying this is x is equal to 0, we're saying now we look at a variable which we'll call zeta is equal to 0, and that zeta is equal to 0 is always going to be on the center of that laser. And so this means we're instituting a change of coordinates. It's a terrible zeta. Let me redo that. X minus v2. All right? So instead of having a frame x here, now we're specifying a frame zeta with respect to where this laser is centered. Okay, just imagine you have a camera that's following around this laser. Okay, so we can write zeta is equal to x minus vt, or alternatively, if it helps us, x is equal to zeta plus vt, just rearranging that equation. Okay, so now we need to apply this change of coordinate to our diffusion equation, right? This is the physics that govern heat transfer for impulse of energy at here, right? So I want to do a quick review of multivariable chain rule because you may not have seen this for maybe like 3 years since you took calculus, right? So let's do a really quick review of this. And so say, for instance, we have a function u of xy, and this function is equal to x squared plus 2y, and then we have x is equal to RT, this is R sine t, y of RT equals R sine squared of t. This is just a made-up equation. By made up, I mean I just took it from Wikipedia, all right? So, but you can find things like this, but just to review, if I want to know what is the partial of u with respect to time, I look at what is u composed of. It's composed of x and it's composed of y. We have functions for x and y, and so the partial of u with respect to time is going to be equal to partial of u with respect to x, partial of x with respect to time, plus partial of u, partial y, partial time. Okay? So if you want to look at this, this is basically, these would cancel out, right? du, dt. Right? Okay, so let me erase that little piece. Okay, so just filling this in, if I look at du dx, right? We have 2x. Right? Du dx, 2x. Dx dt, this is going to be then r cosine t, right? Du dy is going to be equal to 2. Dy dt is going to be equal to 2 cosine t sine t by the chain rule, right? You can think of it as just as sine squared. Yes. Thanks. We got my r, right? Okay. All right, so that'd be multivariate chain rule. All right, so now applying that to the problem at hand, if I want to know what is the partial of u, where u used to be a function xt, right? But I've changed this a little bit, right? I've now said that u, I made a substitution for x. U is now a function of zeta plus vt t. So I want to know what this is, partial with respect to time, partial u, partial zeta, partial time, plus partial u, partial time. And I could just fill this out and say, what is partial time, but that doesn't make any sense, right? That's just one, right? So I'm just going to simplify that. Okay. To go back a second, but if I look at partial zeta with respect to time, right, this is going to give me negative v. Okay, so basically what this has happened before, we had in our diffusion term du dt. With this change in coordinates, now I have du d zeta, right, which is a spatial variable. So a temporal variable turned into a spatial variable times the velocity, and also a partial with respect to time as well. Okay. All right, with that, we're out of time. So we'll revisit this then on Thursday. Also, I want to note that on Thursday, we're going through our first journal article. We'll be leveraging essentially exactly this right here. And in the journal article, it's looking at basically a laser heating up materials for welding. This is kind of the precursor of additive manufacturing. Additive manufacturing is, all the processes just little micro welds that are used to build up something. So we're going to look at exactly these methods for that paper and how this can help explain what the temperature profile is in a weld. Okay, any questions? Okay, see you on Thursday then.